Okay, here we are for week 2. Hopefully too many of you didn't fall asleep last week. So I'm going to warn you that this lecture and the next 2 lectures aren't very exciting. They are kind of snoozy, if you would say, but they're important things that we need to cover. This particular lecture is important because it helps give you a foundation for what we're going to talk about. In fact, most programs assume that everything we're going to talk about today you already have a feel for and you already have an idea for. I don't think that's fair, so I've fit time in to talk about these things just to kind of help you get your head around it. And believe it or not, most of it is stuff you do have an intrinsic feel for. The next 2 weeks, so week 3 and 4, I used to do those as the last 2 lectures because they were slow and easy, not a lot of information thrown at you, but a lot of stuff you need that's going to help you throughout all of your courses. Really just a basic understanding of how the building goes together. I liked that because it gave you the last 2 weeks to be a little bit more freeing. Some of the other teachers have been complaining about what students don't know, but nobody else really has the ability to fit that in, and sometimes not the understanding. Not because that they don't know a lot about buildings, but this is the basics, really, about you guys are learning all about the really cool, awesome stuff, and no one teaches you the boring stuff, like this sits on this and it looks like this. So that's essentially what next week and the week after will be. They asked me to move it up in the program just so that everyone kind of benefits going forward. So you're going to bear with me. This lecture and the next 2 lectures, kind of dry, kind of slow, but then we're going to start to get into some really interesting stuff where we talk about structural theories. And in fact, it's going to go very fast after that. We try to do lots of repetitions so that you get used to doing it again and again and again, and that it kind of takes away some of the confusion from it. So today, we're going to talk about structural drawings. What do they look like? We're going to talk about tributary area and tributary width, and what that means for the elements we're talking about within a building. And then I'm going to give you a quick intro to the project. So there's not a lot of data in this lecture, but there's a lot of interesting concepts. So the first thing I want to talk about is structural drawings. Basically, what do they look like? What are we talking about? I have uploaded for you, there are 2 module folders. One is structural drawings and one is things to download, basically helpful PDFs that you're going to need throughout the course. I try to also put them in that particular week's module so that you know that it's very relevant for that week, but it's not a duplicate, it's not a different file, it's the same file that's just been added to that week's module to kind of highlight, look at me. One of them has typical details, which are standard drawings that usually go at the beginning of every project so that an engineer doesn't have to redraw them. Because essentially they're so basic, the assumption is that everybody knows those particular details or has a sense of it. You might need to refresh yourself, go back, take a quick peek, but they don't need to be redrawn in every drawing set because they're pretty obvious. I spent a big chunk of my summer creating a fake building for you guys that no one would build in real life because it's a horrible design. I am definitely not an architect. But what I wanted to show you was all kinds of different concepts in one building. And then I produced that building as a steel building, and I produced that building as a concrete building to show you what those drawing sets look like and how they differ. I've also provided 2 working projects or built projects that I was the engineer for, where I reached out to the architects and asked if I could also provide you guys with the architectural drawings. You guys have a bit more feel for architectural drawings and what they look like. And structural drawings and architectural drawings are not the same drawing package. It's different information on both of these. The structural engineering package is trying to tell the contractor how to build the building, or what structural elements need to go in the building and where they need to be and what size they need to be and the order they're assembled in. Architectural drawings are more about the space. That's what we're doing in this room. And you have assemblies for sure. There's lots about the building that is very, very, very important in the architectural set. But the structural set has to contain certain information, and we don't want it muddied up with the architectural set. That's going to be important in comprehensive in second year when you produce your structural drawings for me. They are not just your architectural drawings with the structure drawn over them. Sometimes for small houses we might do something like that, but for the type of drawing sets that we're talking about, you need a set of structural drawings, and that's what you're going to produce in Structures 2 for me. So what I've given you for those two projects is the structural set of drawings and also the architectural set. Now, one thing that was really interesting about one of the projects, it's the cube lofts that Raw Architects were the designers for. It lended itself very well to be a steel building, so we designed it and went out for tender, and right at that moment there was a blip in the steel economy in Canada, and basically North America. It was just leading up to the Beijing Olympics, and there was no steel to be found in Ontario, or pretty much North America. You just couldn't find it. You couldn't get it. So steel costs doubled in a week. They stayed doubled for about a month and a half. We went out for tender the week that steel started to explode. Tender came back obviously way over budget. The owner was not, wasn't an easy client to have, and the owner demanded that we redesign the building in concrete. And fair enough, they had had more experience with concrete buildings, and us as the design team had pushed them to steel. We said that the steel market was coming back down and to hold on because we thought that the steel building was the right choice for the project. They insisted that we go with a concrete building instead, so we redesigned the building completely in concrete. It took about 6 months. It tendered. It came back higher than the original budget for the project, and had we gone out for steel at that point, it would have been a much cheaper building, just because it lent itself very well to a steel building, that particular design. The upside is that you guys have the steel and the concrete version of the same drawings. Now, they're not perfectly identical because in that, 8-month time frame from the time we finished the steel drawings to when we finished the concrete drawings, architectural changes were made. The owner kind of revamped some stuff. And now that it was not a steel building, there was some changes we had to make it easier to build as a concrete building. So they're not perfect replicas of each other, but they're a pretty good idea that if you just want something, how does this look? How did these things go together? You can take a look at that drawing package and say, oh, you might not answer all your questions there, but you might have something as a quick resource to help you go back and look at what something looks like. So I have some slides in the slideshow. I'm going to switch over to the PDFs at some point very soon, just so that we have something that I can zoom in and out and talk about it a little bit easier. One of the typical detail pages is basically all the abbreviations, because these come in very, very handy. We talk about them a lot. You're going to see me use them a lot. And I get that you might be thrown off, like, what does this mean? If you're unsure, come back here, because it's probably a shorthand that I've got on here. If not, try Googling it, because probably every other engineer and every other architect in North America uses that shorthand as well. And then if you can't find the answer, email your TAs. And then if nobody knows, definitely reach out to me and we'll figure it out. But some of the common ones are right here. CC or OC means center to center. So that means, my husband keeps stealing my note paper. That means if you have, I'm drawing something, don't worry. If you have a series of wood joists under plywood that I am drawing very badly. You have something like this. Center to center means that we're talking about that dimension right there. So from the center of this joist to the center of that joist. And if we're talking about something that we have a lot of, we might say, 16 or a 2x6 joists at 16 inches center to center. And so we're saying that for that whole floor, every 16 inches you have to have a joist. So they could be shorter than that, but they need to be no more than 16 inches apart. And so that's the CC or the OC. CANT period is cant or cantilever. We're talking about, and you can see it right here in this. It means that there's a cantilever. It is only supported at one end. So a cantilever. I'm drawing a little picture here. If a beam looks like this, it's got a support here and a support here. This is the back span and this is the cantilever. It has to be connected across here in some way to make that work. Or, and you guys are going to learn about this when we talk about free body diagrams in a few lectures, we could say that it is moment connected right here. And that is a drawing of a moment. Moment we have down here, or MC, moment connection, or MOM, we're talking about moment. CA means column above. So that means if we have, in elevation, we have a building and all of these columns come down. We have this building here, and this is the roof, and this is the ground. All of these columns come all the way down, except for this one, and it sits on this beam here. And so in plan, we would say column above. So that's reminding us that that beam is doing a very big job. It's not just supporting the floor, it's supporting a bunch of floors above because there's a column above that does not go down below it. GA often means gauge or the thickness of something, of steel. You can Google, if it says 16 gauge, you can Google what thickness that means. KN, kilonewtons, very, very, very important unit that we are going to use a lot in the next two courses. So this course and your Structures 2 course. KN, I'm going to spend in lecture 5, we're going to spend a good chunk of time talking about what a kilonewton actually means so that you can get a sense of it. But if you see this, you know we're talking about a force. So I touched on MC and moment. Another big one that people tend not to know is OWSJ, or open web steel joist. An open web steel joist is not the same thing as a joist. It's not the same thing as a truss. It is a steel fabricated element, and we're going to talk about this in lecture 4 as well. And I'm going to show you a slide in just a minute, just so you can get your head around it. You've all seen what an open web steel joist looks like, and we use them all the time. You know what? Why don't I draw you a pretty picture? I mean, it's my picture, so it won't be that pretty, but I will draw you a picture. An open web steel joist. I'm drawn very badly. I wish I had like a chalkboard that you guys could be seeing what I'm drawing. It would be so much better. So I'm assuming that there's multiple bays of these. The bottom chord. I am going to show you this, don't worry. Okay, an open web steel joist. This here is the open web steel joist. We've got a top chord. We've got a top chord, which is the top part. We've got a bottom chord, and we've got webs. An open web steel joist means that there's openings in the web of our joist. And so this is usually back-to-back angles, top and bottom, and then with bars or rods built up in between. Look, the top of the open web steel joist and almost the top of the steel beam align with each other, or basically our deck is right there. We don't hang these from the bottom, we don't stack them on top. We do stack a tiny little bit, that's just because an open web steel joist has a shoe. And so we often drop steel beams that are picking up open web steel joists just a tiny little bit. But normally we connect everything, the top of all of our steel is at the same plane normally. R usually means, it can mean two different things. It can mean radius or it can mean reaction. So you have to look at it in context. SOG, slab on grade. And we're going to talk about that in the last lecture. Second last lecture? As well. And then UN and less noted. So, like I said with the open web steel joist. So 2x8 SPF number 1, number 2, joist at 16 inches on center and less noted. So maybe there's a few spots that need something different, but that would be typical, and then this would be and less noted. So that means that everything that was written there applies the majority of the time unless there's a note on a specific thing that says otherwise, and it overrides it. Like I said, we're talking about the loading side of things in structures 1, and then talking about resistance or capacity in structures 2. So we're really interested in things like CF, the factored compressive force in something. TMF, the factored torsional moment in something. TF, the factored tensile force in something. VF, the factored shear force. MFX, maybe MFY, but MFX, factored bending moment. And so all of these little F's means that we've factored them already. And we're going to spend lecture 6 talking about how we factor our loads. So we're going to spend time looking at that explicitly. What does it mean before it's factored? We're going to talk about that in lecture 5. And then lecture 6, we're going to talk about factoring our loads. So here's some open web steel joists. You can see what I mean about the shoe. Normally all of our steel would be at the top of our steel would all be at the same level, except if we're supporting an open web steel joist where our steel beam drops just a little bit to pick up that shoe. But otherwise we connect everything to all be the same at the top. I just want to quickly show you hatching. These are generally the way we hatch things just to make it easy to look at drawings. Different firms might have their own different quirks on it. So I'm just going to quickly look at these. We're not going to spend much time on them. Brick is tight slash lines. Block is large gap between the slash lines. Cast concrete is usually little triangles and dots. Unless we're talking about a very large scale, even larger than this, we might even do just dots to represent concrete, just because it slows everything down. This means you're looking at the section of a beam, maybe a column. Don't worry about this. Mostly I wanted to show you what steel sections look like, and that means if we're cutting the element. So if we do a section that is cutting through something, through our piece of steel, our imaginary cut goes through the steel, we would draw these two little slash lines kind of on a regular pattern across the section to say that that's a piece of steel. It just tells us at a glance that we're talking about steel. Wood, we'll draw little swoopy lines. If we're cutting through a wood beam or a column, we'll cross it like this. This means that we have two pieces of wood screwed together, or two plies of wood laminated together. And then plywood might be 3 or 4 tightly slashed together lines, then with a bit of a gap. I'm going to open up the PDF of typical details and just go through them quickly, but I'm going to go through it at the same time. We might jump back and forth between the basic building I created. Even though there's nothing normal about it, It's a building I created to help us talk about structural drawings. Things that you should always, always, always have on a structural drawing set: grid identification, grid dimensions. In structures too, so many students do not put a dimension anywhere in their project, which means I don't know if the things they sized are correct because I don't know how big it is. I can't even correlate with what they've got drawn on there. Labeling things. Everything should have a name that correlates to something. So you could name your beams right on the drawing, or you could label your roof beam RB01 through RB100, and then somewhere else you have a list of what RB1 through RB100 is. You should show your framing, you need to show your gravity system, and you need to show your lateral load resisting system. We're going to spend some time in the last lecture focused on lateral load, actually in lecture 4 as well, talking about lateral load resisting systems. And anything that's a cantilever, you should identify as well. So like I said, this is a building I've drawn twice, and it's available on Quercus for you. So I'm going to actually switch to the PDF, just because it's a little bit easier to look at. I'm sorry, because my mouse is so large, it's very weird. Like I said, it can be minuscule or gigantic, and that's what I see isn't that way. It's just about the software, the recording software that I'm using. It only lets it register two sizes. I don't even know why, but it only lets it register one of those two sizes, no matter what my screen is showing me. So we have to have the gigantic mouse. So this is, let's take a look. This is a completely average building for University of Toronto. It is a partnership between Imaginary Architects and Faith Associates. And it's a partnership for super totally awesome made-up buildings. So this particular building, this is the steel version of it. I also have the concrete version of it. My ultimate goal is to make sections throughout the building for you as well, but this took time I did not have to make as it was. I might try to get some sections thrown in for this. We'll see. I thought I was in good shape this week to make those sections for you guys, but project just went sideways that I have to deal with some stuff for. So that's going to steal like 40 hours of my week this week. So I'm not going to get to cutting sections for you guys for this, but it's not needed. I thought it might be nice to have for them. So let's zoom in. Let's see if I can get this even bigger here. This will have to do. So this is our foundation plan. And like I said, you guys can be looking at these on your bigger screen if you want, if that's helpful. So this is the foundation plan. We've got grid lines, A, B, C, D, 1, 2, 3, 4. It looks like they go through the center line of something. I'm going to tell you that it's going through the center lines of the columns. For steel buildings, it is very helpful to have your grid lines go through the center lines of your columns and reference everything off that. The architectural grid lines are going to match, and they're going to go through the center lines of columns, and then everything would be dimensioned off of that. You can see that we're looking at the foundation, so this is what's down in the ground. Now, the way sections are cut for plan, often, so there was kind of a change on this since I've been working. I do them all the same way. Actually, I don't like that section that I just drew there. The way we tend to draw our buildings is cut looking up, or what we call a reflected ceiling plan of the structure. And that's very handy because it shows us what our columns are going through. Concrete sometimes is cut looking down, And it can be very, very, very confusing because we're showing columns not aligned with the things we're looking at. We're not looking at the framing for that floor. So there are pros and cons with both things. I have consistently found that cutting and looking up is the way to go, and most other firms around North America also do that now as well, whether it's steel or concrete. But you might still find concrete drawings that show the opposite way. And I'm just going to show you what I'm talking about. So if this is a building with a roof, a second floor, a ground floor, and a basement, our steel plans are cut looking up. So I would show this column cut and the framing for this floor. So these beams, you can easily see, are supported on these columns. What people often used to do is cut looking down. So this cut here would show this column and this framing. Now that was confusing because this column isn't supporting this framing, and if we had a column that stopped and started, for example, let's do an example. Let's put a column right there. We easily see our column above because we're cutting through it, but we don't know where our columns below are. We don't know where the things are that are supporting that beam. So we've switched, and instead of showing columns below as a note, we show our columns, we cut the columns that are supporting the floor we're looking at. The only exception to this rule is foundations. We will often still, for foundations, cut and look down. So a building with these stories that has a foundation or a basement, a ground floor, a second floor, and a roof, we would cut and look down at our foundation right here. We would cut through those same walls and look up at that framing. We would cut through these columns and look at that framing, our level 2 framing. And then we would cut through these columns and look up at our roof framing. And that would capture all of our scope in our drawings. And this is the process that I have done for these drawings. So this is the foundation. So it is cut and looking down at our foundations. So that means we are cutting through our walls, so we should hatch them, and we're looking at the footings below. So we're not hatching them, we're looking at the outline. So you can see here that I've cut through a wall, and there is the footing below. And there is our strip footing right here. In light coloring are notes that would not normally be on the drawing. There are things I've included that I think you might find helpful as a note to see what the wording is. So this is dark. This would actually be on the drawings, and it is a datum. So here I've let you know that this is the underside of footing in geodetic values. It varies because of basements and pits, but could also vary due to geotechnical data. Sorry for any typos. This is a note that would actually be on the drawings, and it says 200 conc, which means concrete wall, width 15s at 400, horizontal and vertical. So within that wall, there's reinforcing that is vertical and reinforcing that is horizontal, and they are 15 millimeters in diameter, and they happen at 400 millimeters center to center, and a 400 by 200 footing with two 15 continuous dowels, two 15 M's continuous, dowels to match, typical unless noted. So that means we have a footing with rebar that's running consistently through it, and there are dowels to match our wall footing within that wall. So this one note is probably 90% of the scope on this drawing. That one note captures almost all of the cost of this floor. This this zone here has a note that says unexcavated. So that means in that building that we've drawn, we have a zone that seems to have a basement and a zone that doesn't. So I'm drawing just a new little section. And this is the stuff that I would have loved to have gotten in the sections for you guys. So this over here is what we're looking at, and we're looking at these footings right here, and this zone is unexcavated because we are making a cut looking down like this. So we are looking at that wall and that footing, and then we're going to come over here to ones that are deeper with some sort of slab, and we'd be looking at this slab right here. So this zone is unexcavated. That doesn't mean that they don't take some of the soil away, but it would be backfilled wherever they had to dig away soil as well. So this zone is unexcavated because there's no basement, likely at least partially excavated and then backfilled to support slab on grade above, which we will see in the ground floor drawing. This is inside an insulated building, so this column can be up pretty high, or that footing can be up pretty high. These ones here need to be down at least 4 feet for frost. They can be pretty high up because they only need to be down 4 feet for frost. But over here it looks like we have a basement. We can't have our footing go along and then drop a bunch and keep going. We need to slowly taper that footing down to get to the new level. So we will often include this note that is SDF, or step down footing. That means that at this point we are dropping down to a new datum, and then we're dropping down again to this datum. So up here we were up pretty high, and then we slowly dropped down to this zone here. Now this is a basement, and this is the floor of the basement that we're looking down at. This says BS01, or that's a reference for me to know that I'm tracking things, but most people are pretty consistent, and you can probably infer that this means basement slab number 1. 150 slab on grade with 152 by 152 welded wire mesh, coordinate saw cuts with ARC, but no more than around 2400 center to center. So I've drawn some intent of saw cuts, and that is to help control cracking in the slab. Get your head around it, concrete cracks. Always, 100% of the time, concrete cracks, but we can do what we can to try to help control where the cracks happen. And that's what these saw cuts are. Saw cuts help control slab cracking. It does not eliminate it. Tell every single client. Probably, I'm my own company, so I don't have as much, I'm not doing the massive projects, but my husband's company, Blackwell, especially when I was working there, I knew more about every single project that was happening. Probably 50% of the lawsuits they get are from clients who do not understand that concrete cracks, and they sue because of it. They say, oh, I have big cracks in my concrete, I'm going to sue you. Even me, I have a project that is going right now that the concrete cracked. I told everyone at the very beginning, the concrete's going to crack. We can do what we can to control it. We can try to control it even more by putting more rebar in it, but nobody wanted to. They said it was too expensive, so we didn't. And now the client, the contractor, and even the architect, who all knew about this, are saying, why is my concrete cracking? Luckily, I had those emails, not because I want to make them look foolish or anything, but I kept those emails where I reminded them what we do for concrete cracking. And so the issue went away. But if you tell your client and document it, you will probably avoid some lawsuits that are, let's face it, kind of frivolous ones to begin with. So here we were looking down, we were cutting our wall, and we were looking down at the outline of our footings. Here, my footing line changed to something dashed. And that is because right here, this part of my footing has the slab coming across the top of it. So I'm looking down through the slab on grade to look at the outline of my footing. Understanding these kind of habits in drawings is very, very helpful. You can extrapolate a lot of context by knowing that that's a dashed line and it means that my slab comes above my footing. That is most of the information over here. Let's come over here to this zone right here. Okay, so this is an elevator pit slab, 200 with 15s at 300 bottom each way. So elevators often have a little pit that come down about 5 feet below the level. And that is usually there's electronics or a motor, or that's a work shaft, that's a safe spot that somebody could crouch down in if the elevator came down. There's all kinds of different, sometimes it just drops down some, but 5 feet is standard below your slab that's right here. So this is 1540 below this slab, so that's 5 feet. And we often just make it, rather than strip footings in a slab, I have made it match the footing. So the elevator pit slab is basically just a big portion of footing, and it's got a bit more reinforcing in it. Sometimes they have like a post in there. Sometimes there'll be a sump pit in there as well. This is my stairwell. I have a sump pit in this stairwell. That's where the water would drain to, and then there'll be a sump pump that actually pumps the water out. The exterior wall below concrete stairs is a little bit bigger. I've made it 300 with 15s at 400 horizontal and vertical each face. So now instead of just horizontal and vertical rebar, there's horizontal and vertical rebar at each face of the wall. The footing is a little bit bigger as well. And you can see that I've shown some context for the stairs. For this stair, I've said it's cast in place stairs and landing. Refer to typical details, coordinate with architect. You could do steel stairs here, you could do cast in place. You could do precast stairs as well. I wanted to show you something, but you can see here that this says plus 1080. So that means you come in a door somewhere. So that we're looking down at the footing below, but there'd be a doorway in here somewhere. And you would walk up the stairs, and there is a thickening in the slab below the stair support. And you would walk up the stairs to this landing and keep going up the stairs. Let's pop over to the typical details. Oops, that's the wrong. I haven't been moving my mouse on the wrong. No, I haven't. Okay. Pop over to typical details here. So here's the abbreviations. Rebar lengths, how long rebar needs to be to lap each other. Don't worry about this too much right now. Here is here are our footing details. So we have the underside of our footing. That's what was called up. You can see that this would be how thick our footing was, and here is the elements that are coming onto it. Here are those dowels that I was talking about. So they'll come and they'll pour this footing. And rather than have these big long pieces of rebar sticking up, we have smaller pieces called dowels that stick up out of it. And then they form this and put this rebar in and cast the walls. The amount these two things lap are called our development length. And that was that last slide that we just looked at. These are going to be the footings for our steel columns. We have a steel building, so we know that this is probably applicable for us. There's usually a pier, and then something that looks like this. There'd be a slab and a column base plate. Wall footings. So this was that step down footing I was telling you about. So this is the underside of the footing right here. So there's our footing thickness. We can't just drop straight down. We do it in increments, sloped no more than 7 to 10. And we can only do 2 meters at a time. If it's bigger than 2 meters, we have to have multiple step down footings, which is what you saw, very slow, sorry, which is what you saw here. We had 2 series of step down footings right here. Sorry, it's been busy out on my street right now. Do you guys want to see? I wonder if you guys can see my view. Oh, it's probably too bright. No, it's too bright. Yeah, it's a beautiful day out there, and I just wanted to share my luckiness with you guys. But maybe I'll take you on a walk out there later. We have notes here. It says basement floor datum elevation is 0. That basement floor datum elevation is at geodetic elevation 205. So there's something in the architectural set that says what these datums are, and everything is referenced from that. We're cross-denoted the local datum for raised or lowered areas are given relative to the basement floor datum. So that was our elevator pit, and our landing and our stairs were given relative to the 0 node. Except as cross-denoted, top of finished floor is 0 below the basement floor datum. So that is our floor plane. Where cross-denoted slab depressions or locally raised areas are given relative to the basement floor datum. So maybe we have a curb or a housekeeping pad, or maybe sometimes we'll notch the concrete down an inch or 2 to inset a grill for like a drip plate for muddy boots. Found footings at the datum shown as noted. All footings to be 1.22 meters min for frost protection. So we need to be minimum 4 feet, but you also need to, so you can be more than that, but you have to be down that much. And that's just a standard note that goes on every drawing, so no contractor can ever claim they put their footing in the frost zone in southern Ontario. There's also a note, found footing on soil capable of supporting ULS 150 kPa and SLS 100 kPa. There's a soils report that goes with the project that tells us what the soil capacity is. Now, soil testing isn't perfect. They are testing a representative sample of the site. They often usually need to be there and look at the footing before it's cast to make sure that it was all what they expected it to be. This note is here in case they find a patch that is not good enough. So all of my notes are based on the geotechnical report, the imaginary geotechnical report for this project, but the geotechnical report that said good soil is at this level and you can do this. If they found on site that, you know, maybe I have a project right now that there is an old well that no one was expecting right here. So we needed to know, do we dig down further and lower this footing, or do we do something right there? On this particular project, they're filling it up with basically cheap concrete. It's called lean mix. It's stronger than the soil, but it's not as good as normal concrete. So it's a kind of a cheap way to fill it up, especially when it's a massive old well that they need to fill up. Sorry, I went for a 10K run today, and it's the most I've run in a very long time. So I am sore, and I'm tired, and I'm very, very thirsty. So these are just some notes that I wanted to add to expand on that. I might have even covered all these. Okay, so this is just a note reminding you that they're cut looking down, dashed because we can't see beyond, hatchet if we're cutting through it. Look, great, I covered all of that. So now let's jump to our ground floor framing plan. So ground floor framing plan, we're cutting through those foundation walls again, but now we're looking up. And what's handy about that is any framing we have here, we're showing it what it's sitting on. We're showing what's supporting it. So these walls are supporting anything we have, and so we actually get to see what is supporting our structural elements. So let's maybe start with the notes. ground floor datum is at 0, and it's at geodetic elevation 208. So it seems like 3 meters above our basement datum. So our basement was 3 meters. Cross-denoted, local ones are relative to the ground floor datum, except cross-denoted, underside of deck is 0 below the ground floor datum, and top of slab on grade is 0 below the ground floor datum. So there are some interesting notes here. So that means I have a step here. That would be a thing I might change here, but often concrete, we're talking about the top. Unless it's a topping, steel, we often reference the underside of metal deck. So if it was our concrete slab on grade, and I'm going to draw 2 different drawings here. Sorry guys, I know it seems like I'm being weird looking down here doing this, but I don't have like a means to draw this. So for a concrete building, we often do our datum to the top of the concrete. For steel, we often do our datum at the underside of the metal deck. So that really what we're saying is the top of the steel, but then we have those pesky steel beams that drop because of open web steel joists. So we tend to reference the underside of metal deck. I made both of those 0 here, which means that I have a step here. Not a problem. Maybe that's what I intended all along, for there to be a step between these sides of the buildings, but it would be something I'd need to capture in a section, because the underside of this metal deck is at 0, and the top of this is at 0, which is essentially saying I have concrete on metal deck here with some sort of closure angle, but my top of concrete is here with a wall. There'd be more to this detail than this, but here is, they're both saying that they're at the same datum. So my underside of metal deck here and my top of concrete slab on grade here at the same datum, which means whatever this thickness of assembly is how much this is raised. So maybe I should tweak that for this. You wouldn't tend to normally have both of these kind of on the same spot at the same time. So I would leave it like this. If I draw a section, I'll leave it specifically to show that weird interface for you guys. Cross-denoted slab depressions. Top of steel beams are relative to the ground floor datum and are indicated in the beam schedule. So that seems like there's a schedule of some sort that tells us where these beams are. Well, that's handy. So we have something that talks about beams. We've got a beam schedule here. Loads used in the design. This is going to be very handy for us. Live load. We're going to be talking about what these loads are in not next week's lecture, in lecture 5. Typical ground floor dead loads. So this is how heavy everything is that makes up our ground floor. Refer to structural drawing set for general notes, typical details, and schedules. So it's reminding the contractor that they have to look at this package all together for it to make sense. Let's take a look at this floor plan. Remember, we're cutting through the walls and looking up at our framing. Well, this zone over here is a slab on grade, because remember that was an unexcavated zone. It looks like the information is very similar with some saw cuts in it. They've given us notes that there are columns above here, so somewhere right above here our columns are found. This zone here had a basement, so we need something to make up the floor here. So we have an assembly of things. We're gonna have, the flooring, what the architect specifies, sitting on a slab of some sort or a deck. And that's the thing that covers every square bit of surface. But then that needs to span and be supported by something. That's what we would often call purlins, or open web steel joists possibly. And then those would often span to beams or walls or columns. So here we've got GSO2, or ground floor slab O2, because this was ground floor slab O1. This is 64 concrete on 38 metal. What they are saying is that, I have not drawn this to scale, so don't fret about that, that we've got 64 millimeters of concrete on top of 38 millimeters of metal deck. We're gonna look at this again, don't worry about it, you do not need to know all of these things. We will talk about it more. There's a whole portion of a lecture where we talk about steel and kind of the bits that make up our steel framing. So that means it's a total of 102 millimeters. So the underside of this deck aligned with the top of this slab. So it seems like we have a 4-inch step from this side of the building to this side of the building. This concrete deck, or this concrete on metal deck, spans in this direction. So the flutes are running in that direction. So it's, if you picked up a piece of corrugated cardboard, in one direction it bends really easy, and in the other direction it does not. Well, we are taking the direction that does not bend easy and spanning it that direction. Even though it's one big thing, bits of it are being supported by bits of beams. So this beam here is supporting, can I do it for me? Is supporting, well, that's not very helpful, is it? Let's make that a color. Let's make it green and green. So that beam right there is supporting that much of that portion of deck and that much of that portion of deck. So that is something that we would call a tributary width, and that is the length of the beam, but the entire tributary area is that zone right there. GBO1, it looks like these are all the same beam, and it says GBO1 is a W250 by 39, so that's a type of steel beam, or ground floor beam O1 is a W250 by 39 at 1900 max tip. VF equals 65 kilonewtons. So they've given us a factored shear force in kilonewtons. They've told us what the beam is and how often it needs to occur. They can be closer spaced than 1900, but the maximum distance between one of these beams is 1900, or the maximum distance our deck can span between supports is 1900. We have our stairwell over here. It looks like the stair over here now has steel stringers. We've got a doorway to get in. We've got another landing that we can come in and go up. There's our stair going down. There's our stair going up to a landing, and it keeps going up to the next floor. This looks like these are steel stringers, which means that this is a steel stair with some sort of pan construction on it. If you've ever, actually, for those of you that have been in one Spadina, which is none of you, I guess, at this point, the stairs have this style of construction, so you can see it, but you've probably mostly seen that style of construction. Let's go to level 2 framing now. So we're going to look at something cutting between the ground floor and level 2, looking up. So we'd be cutting any of the columns that go from the ground to level 2, and we're showing the framing at level 2. So it's supporting everything on level 2. Level 2 floor datum is 0, and its geodetic is 211. So that means it looks like we're another 3 meters up again. Cross-denoted for local datums, except for cross-denoted underside of deck is 0 below the level 2 floor datum. So underside of metal deck is our datum, except if it's cross-denoted and says otherwise. Where cross-denoted, slab depressions or locally raised areas are given relative to the level 2 datum. Top of steel beams are relative to the local datum and are indicated in the beam schedule. So we would come over here to our beam schedule for the tops of those beams. And then we have live loads. Ooh, look, and snow loads. Ooh, and interior dead loads, and a low roof dead load, and a balcony dead load. So it looks like in different zones of this building, we have different loads. Not all the same load is everywhere on the building. And this part of the building sees different loads than this part of the building. So we have our interior space, we have live loads that are indoors and on balconies. We have snow load, ASL as shown, or accumulated snow load as shown. Sometimes they'll just give us a snow load that has already been designed. So they've already taken the information I'm going to give you in lesson 5 and manipulated it to find the total. And then you guys are going to see that I'm never going to make you calculate accumulated snow loads. I'm going to make you calculate snow loads, but I'm not going to make you calculate accumulated snow loads. And so knowing if it's been calculated or not, forgetting accumulated snow loads is very important. If you see SS and SR, this will make sense in lecture 5. You need to do something with it. If they just say the snow load, they've already done something with it. And that's going to be important when you work on your projects. The interior dead loads have floor finishes, 64 concrete on 38 metal deck, purlins or open web steel joists with a load, steel, they've given us a load, they've given us a mechanical and electrical load and a suspending ceiling load. We're going to talk about all of that when we do dead loads in lecture 5 as well. And then we have a low roof and we have a balcony. So it seems like this is the interior of our building. And over here, something is crossed and noted. Let's see what this crossed and noted thing says. It says minus 250 for the underside of our metal deck. Ooh, they've given us a total snow load. So it starts over here and comes down, so it tapers down. They've labeled this deck as 38 metal deck spanning in this direction. And we have purlins that it's sitting on. The difference between beams and purlins and girders is going to be important when we talk about steel. And I believe that is lecture 6, yeah. Yes, lecture 6. We're going to need to know about that. Don't worry about it too much right now. Just know that it's a type of beam. It's a beam. This dashed line here tends to be an open web steel joist. We tend to draw this line when it looks like this. It usually represents an open web steel joist. And look, they said 2J01. Gives us a pretty good feeling that it's an open web steel joist. This drawing, very much on purpose, I wanted to show joists and beams and purlins doing our floor framing. Because they're essentially the same idea, the same concept. We have a concrete on metal deck spanning this direction. And over here we have a balcony. Ooh, look at this. Cant. That means that's a cantilever. See this solid colored black triangle? That is indicating a moment connection. It's another way to indicate a moment connection. And so right there, we are saying that this beam is moment connected to this beam. But the beam might not be the same beam. It might change. So they need to weld it up together in some way. Ooh, over here, there is a note that says column above. So this beam goes from C all the way over to A with a point load coming down on it. That seems like it's a hefty load on this beam. This one does the same thing. So column above between second and roof impacts beam, so it's helpful to see it even though we aren't cutting through it. So that's not one of the columns we're cutting through because it's up above what we're looking at. But it's nice to know because at a glance we can see that there's something big and nasty happening to this. So there's no column below. This is not a support of this beam. This beam is supporting this column because they've told us that this column does not continue down. So this balcony cantilevers out. Our stairwell here has switched to be masonry block lateral load resisting system, or LLRS. Walls will have 15 at 400s grouted solid. Refer to typical details for lintels. So I will switch over to typical details and we'll take a look at some of this stuff. Stair and landing designed by supplier, contractor to coordinate bearing pads. So we've got steel stringers. So this is the same as what we had below, framing into our masonry block. Let's switch over to some of our typical details that might take a look at some of our steel framing now. We'll come back and look at the concrete ones when we look at the concrete building. This is lintels for masonry. Look at this. Here are the lintels that we would need to frame those openings in the block for a doorway. That's a lintel. Here are some good details. Concrete slab on deck, framing details. So look at this. We've got our metal deck, that's 38, 64 thickness of concrete, even though the concrete comes down in these flutes. We have, that would be our datum. Our open web steel joist aligns to the underside of it. And then we've got a steel beam supporting the top chord of our open web steel joist. And it's dropped a little bit. Now, if this wasn't an open web steel joist, this would be slightly different. This would be pushed up to the underside of the metal deck as well. I'm going to show you a detail of that in just a minute. But this is a pretty handy thing to have in your head. I see people draw it with the open web steel joist sitting on top of the steel up here. That makes a very thick assembly. That is not what we do. Metal deck being supported by masonry. Let's not worry about that too much. Do we have just a typical detail of steel? Interesting. We don't just have, I don't have a basic steel detail. Okay, well I'm going to hand draw you one right now. We will see more of them throughout the lecture, so don't worry, throughout the course, so don't worry about that. For a typical steel connection, we might have two separate beams. That look like this. So we have our metal deck, and we have our purlin, or it's just a type of beam that is doing a similar job to an open web steel joist, and another beam. So look, both of them are at the underside of the metal deck. See, we've coped our steel beam, which is not a big deal, they do it all the time, and then connected into the side of this steel beam with a clip angle. So let's go back to our drawings here. So that was our level 2. Let's take a look at the next. Let's take a look at the next level. We have our roof framing plan now. So our roof framing, we've got our datum that we call up, referencing off of our datums. Roof is sloped to drain. Deck and beam local datums are relative to the sloped roof. So they tell us where things are sloped to. Sometimes we can make it all flat and they'll slope it with insulation, but if you can and it's easy, you might as well slope with your steel. Let's take a look. How did they slope it? Well, it looks like that's 0 and that's minus 150. So it looks like that beam goes on a bit of an angle. You guys are backwards to me, so it's throwing me off. It slopes on a bit of an angle. Not much, just enough that if they put a roof drain right here in the deck, and they probably run it down along the side of the column, they can get their slope almost for free without using insulation. Top of steel beams are relative to the local datum. We have our snow load. So see, look at this. Snow loads. 1.12 kPa plus ASL shown on plan. We're going to talk about this when we do snow loads in lecture 5, but this means somebody has calculated the snow load for us already. And they've shown us where the snow loads are. This is not SS, this is not SR. Again, that'll be clear in lecture 5, but pin this in your mind for talking about the project. This is the snow load. Somebody has already figured out what the right snow load for this building is. There's the dead loads, and just a reference to look at the full drawing package. So there's not many surprises here. It's pretty similar. We're showing our bracing or our lateral load resisting system, which means that we have something stopping our building from tipping over. This would be our lateral load resisting system in elevation. So it's the thing that stops our building from tipping over. It looks like we have 2 lateral load resisting systems. We have steel bracing and masonry block over here around this elevator core. We're going to talk more about lateral load resisting systems, don't worry. Let's take a look at the schedule. So here is the mark. We've labeled what everything is, and then we've said what that section actually is. They've given us reactions so that we know how much we need to connect these things from sliding down away from them, and they've listed top of beam. Oh, look, 2B11 is minus 100. Cope top of beam at low local datum and reinforced to match. Okay, so let's take a look at 2B11. Let's see where 2B11 is. That was on level 2. 2B11. So it's picking up open web steel joists, so the top chord needs to be dropped 100. So that means then we have these purlins and these purlins over here that need to connect into it. And it needs to support this deck right here. So this is where they've told us to cope it down somewhat. So the top of that beam would go along and then is coped and reinforced at that level. There's notes for the beam schedule. There's the roof beam schedule. Let's take a look at the column schedule. So the column, let's A2. Let's find A2. All right, so here's A2 right here. So it's right at the corner of our building, column A2. Well, it doesn't look like we have a column from roof to level 2, but that's where we had the low roof portion with no upper building there. Let's take a look on the plan. Yeah, there was no building here and here, or there was no roof above here. So you can see that there's a low roof, but then nothing here. So it makes sense that there's no column there, and that the column really starts right here. So they've drawn it. They've said what the underside of base plate is. So there's an indication of how long that column is, and what the size is, and what the factored compressive load on the column is. They've said what the base plate size is, how we need to connect it to the concrete. They've given loads for the footings, and then this says refer to plan for the footings. Let's come over and take a look at A2. Oh, yeah, sure enough, There is a footing here. There's no information, but look, oh, tip unless noted. 500 by 500 pier with 8 15s vertical and 10s at 300 ties on a 2000 by 2000 by 300 footing with 8 20s bottom each way. So a grid of reinforcing in the bottom of that footing. Dowels to match, tip unless noted at steel columns above. So all of the steel columns have the same footing. Oh, that works. They all have that note here. So that works out just fine, except for these ones, which are just columns above. So those were our columns above that loaded, for example, our 2B11. So that's the steel building version of it. Let's take a look at it in the concrete version. So a lot of the information for the foundation plan looks the same. Not much changes because they were both concrete foundations. One of the things that's interesting to note is look at where the grid lines are now. For concrete, we don't want our concrete walls jogging around in the building. We usually fit our steel inside the envelope, so it moving and having a center line isn't a big deal, and the walls stay the same, and we fit it inside it. Concrete, we want that outside wall to stay the same, or else it's going to look very weird, or they'll have to do weird cladding things. So we change our grid lines to be the outside walls, and then for interior grid lines, centered on our column is a good way to do it. So we have slightly different grid line dimensions, but the overall same outline of our structural building. Most of this stays the same. One thing that's interesting is our pier has gotten bigger. We're going to have concrete columns, and concrete columns are bigger than steel columns. So we probably should leave a bigger pier here to be able to pick up the bigger thing. Our slab on grade is the same, or our unexcavated part is the same, and our slab on grade is the same. Even most of this is the same. Let's come over to our ground floor plan. So one big difference here, our slab on grade here, same deal. The one big thing is instead of metal deck running this way and beams or purlins running this way, we've combined those two things into one thing and made it a 300 slab spanning in one direction. It's got 15s at 300 top and bottom each way. So a grid of reinforcing top and bottom. And we're saying that the slab starts here and ends here. It covers this whole zone, but most of the load is going to this wall and most of the load is going to this wall. Or its tributary width, half of it is coming over to this wall and half of it is going over to that wall. Let's take a look at our level 2 datum. So this is where it starts to get interesting for concrete. Our top of concrete is our datum. We've talked about this. Our framing with concrete, this is one of the great things about concrete is, I really jumped all over all of this. The great thing about concrete is that you can often tuck at least part of your structure into the slab that you already need there. So if I was to do a section of a slab that had a beam in it, and I showed you this, and this is the slab, and this is the beam, my beam is actually all of this zone. So I can tuck part of my beam up in the slab. So this is cut looking up. So we are cutting between the ground floor and second floor. It's bugging me then that these lines are dashed because we're cutting looking up. So we should be showing these as solid lines because we're seeing them as solid lines, not not dashed lines. I think I probably have a note somewhere that lines are shown dashed for clarity, just to kind of help your eye see it. But we are cutting, looking up at this level 2 slab. What we're seeing is a 250 two-way slab. So that means all of the floor is a slab, but instead of just spanning in one direction, some of this slab is spanning over here, some of it's spanning here, some of it's spanning here, and some of it's spanning here. In this zone, it looks like we don't need a beam, but we'd reinforce that slab more there. Over here, we have that big column above that we had because the outline of our building changes. So we have a major transfer beam, so we need a 1000 by 1050 beam to pick up that column above. So there's a big load there, so we need this beam that spans from column to column, and then we're indicating a column above here that's coming down on top of that beam. Instead of block, we're doing a concrete building, so our stairwell above grade is also going to be concrete. I just make a note to be consistent with your labeling. You can take a look at these and read through these drawings as well. You have these PDFs. And then our roof, we are saying that there's beams here, but they're able to be within the depth of the slab. So, as much as I said that was a beam, we can have zones as well where that is actually a beam, where we reinforce a portion of the slab to act as a beam as well. So that's what's happening here. We have drop panels. I showed you those failure videos of failure images of concrete, and I said that shear is really one of the tough parts of concrete. And so our slab wants to slip past our column. And what we do is we basically make a little ledger for our concrete beam. So if we were looking at a section of this, this is the top of our slab, we would be looking at something like this. This is our slab, this is our drop panel, and there's our column. So that it makes this harder to slip down around it because it's so much thicker right here. It's a lot harder for that to slip past the column. Let's take a look at any more of those typical details. Let's go back to some of those concrete ones that I skipped over. All right, so here we had one-way slabs where they talk about the reinforcing, how that needs to look. So my drawings look pretty simple because I know that this typical detail would be in the drawing set. Two-way slabs. So there's reinforcing working hard in both directions, and we say that this is acting like a beam in here, and we put extra reinforcing in there. Flat slab with drop panels, so you can see that these are the drop panels like I had drawn, and they talk about how reinforcing behaves in the slab because of that. This is a bit beyond what you guys need to know for right now. I just wanted to show you that there is information on this in all of the data I've given you. Holocore is another assembly where we get rid of purlins and concrete on metal deck and replace it with a slab. But it's a slab that we bring in and drop in place rather than casting it in place. And we're going to talk about that going forward. But you can see we have some typical details of what that looks like. Let's go past the steel ones and look at some of the wood ones. So there's wood typical details in here too about wood, what basic wood construction looks like. So these are things you can take a look at and flip through as you want, or to get ideas of how assemblies go together if you find that interesting for you. You can see even here, here's a foundation wall with a brick veneer, and what the wood framing would look like there. So these are all uploaded for you to be able to have a look at. Let's come back to our presentation now. So we've gone through these slides. I'm not gonna go through them again because we just looked at them through the PDF. And then we went through the typical details. I've talked about the 2 drawing packages for you guys as well. So I want to introduce this concept of tributary area now. So tributary area and or tributary width is the area of load that impacts the design or deflection of a structural element. So it is all of the zone that the thing is supporting. In principle, it's very easy, and most people, I think, intuitively get it. If I took a look at that table right there, you know that each corner or each leg of that table is picking up 1/4 of that table's area. You understand tributary area. So in concept, that's a pretty easy thing to understand. We have our whole big table, and the table is the table weight, so it's all going evenly to each corner. What if I just sit right here over this table leg? Where is my weight going? You guys probably intuitively understand that pretty darn near 100% of my load is going to this leg. Those 3 legs, each picking up 1/4 of the table weight. This leg is picking up 1/4 of the table weight plus 1 Shannon. So load is not necessarily the same everywhere for every load type, and that is really important. People have a really hard time getting their head around it. Most of the time, if we're talking about something pretty simple, we're talking about the load everywhere. So what we do is, instead of saying Shannon's going to sit right here on this table leg, we would, designing this, say, you know what, there's a pretty good chance there could be an assembly of Shannons everywhere on this table, and that's when we talk about our live loading criteria. And I'm going to show you guys that when we look at live loads in a couple weeks. Ooh, I'm just getting a package delivery. Okay, so let's keep going. So I'm going to introduce this concept of tributary area, and then I'm going to do some calculations for you guys, kind of just showing us what that means. I find one of the good ways, or a good way to kind of get your head around this, is to talk about a watershed, or a tributary, or a river system. You guys tend to get your head around that pretty easy. And the reason I like this is because you guys understand that if it is a snowstorm, okay, let's talk about the Mississippi, for example. The Mississippi watershed starts in Ohio and comes out into, what basin? What big thing? I can't remember. The Gulf of Mexico. So its tributary area is massive. Hold on a second. Awesome, thank you. So you get that the tributary area for the Mississippi watershed is enormous. If there is a snowstorm in Ohio, there is not necessarily that same snowstorm in New Orleans, which means that that snow load is only impacting a certain zone of the tributary watershed. So that one load may be very applicable in that zone, but it doesn't mean it's everywhere at the same time. So if you were walking in the woods and you came across a river in the forest, you would look at it and say, whoop, that's a river, and you wouldn't think anything more of it, and you would go back home and that would be the end of it. If you were walking through the woods and you came across a creek, you would say, oh, there's a river, and you wouldn't think anything more of it. But if you were looking at the system, if you were looking at that creek relative to the river, you would understand that it is the smaller element, or it is picking up less zone potentially, or less watershed than the river. They're all rivers, they're both rivers, but for our own mental kind of ability to give them a hierarchy, we give them different names. They are all rivers. Let's look at a stream. You come across it in the middle of a forest, you're still probably going to say you came to a river. But you might designate that a stream if you knew that there was a creek and a river in that watershed. And then maybe we've got something even smaller like a brook. So this is important because you could have a snowstorm over here, and you could have a rainstorm over here, and it could be sunny over here. So this brook here is picking up a certain amount of rain load. This brook over here is picking up a certain amount of snow load. This river is picking up this rain load and this snow load. So you have to look at everything above the element you're thinking about. This one's pretty easy. You're going to start right here. But down here, you need to think about what all of these are potentially doing. You might make it easy and say it's snowing everywhere right here, and that is my tributary area for rain. And maybe it's snowing everywhere right here, and that's my tributary area for the snow, and nothing is happening right here. But you have to be able to break that down. And look, just because I've called this a brook and said that then there's also a stream, it doesn't mean that brooks only go to streams. Look at this brook. It's going directly to a creek. And streams don't need to go to a creek before they go to a river. You could have a stream go directly to a river. You could have a brook go directly to the river. This is simply about trying to give ourselves a hierarchy to allow ourselves to communicate what the roles are doing. So, for example, this might be the tributary area for our brook. Are they okay?
Yeah. I need coffee and then I gotta buy my tea.
Okay. Would you also fill me up a glass of water?
Sure.
You're the best. So this would be the tributary area for the brook. It doesn't matter what zone of rain or snow is, if it falls over this, every little bit of that is getting it, and it's going into the brook. That is the tributary area of the stream. That might be the tributary area of the brook, but this entire system is the tributary area of the river. So this is a really good analogy for what happens in buildings, and I think people intuitively get it with a watershed system that helps it. Oh, I have a cup. All right. I'm sorry. Thank you.
Yeah.
So let's take that same analogy and think about it with a building. What if we called the river our columns? And what if we called the next biggest thing a girder? That doesn't mean only girders frame into columns. Then we might have beams and we might have purlins. But a purlin could frame directly into a column. It could frame directly into a girder. Purlins, beams, and girders are all beams or rivers. Columns are slightly different in our building. That's maybe where the one flaw in the analogy is. But you could have a column sit on top of a beam as well. You could have it frame into a girder if you wanted. So it's more about giving ourselves a means to talk about these things. The labeling doesn't mean that there's anything... we're not trying to say it's doing a different type of job. We're saying it's doing a different amount of job, if you will. So a purlin is a type of beam that's maybe doing a little less work. It's still a beam, but it's maybe not working that hard. And A girder is still a type of beam, but it's a type of beam that's working really hard. It's doing a bit more than what our beams and purlins are doing. And that's going to be really important when we talk about our sizing guidelines, because having a feel of what sizing guide you need to apply to a steel beam comes directly from this analogy. And I'll explain what those roles are for each of those when we get to it. And maybe this column is picking up the 4th floor and the 5th floor, and the 5th floor live is different than the 4th floor live load. So saying that the live load on the 5th floor is 4.8 kPa doesn't mean this entire zone is 4.8 kPa. It could be 4.8 here and 2.4 here, and we need to break that down and think about what that means for the column. Again, we're going to talk about live loads in Lecture 5. So let's take that same analogy and look at it again, but maybe draw it as a building. So if we said our columns were our big major element, and our girders were a type of beam that are doing a lot of work, and our beams are a type of beam that are doing our normal everyday amount of work, look, the girder is picking up the beam. And our purlins are a type of beam that are maybe doing a little job. And in our case, they're the ones that are usually picking up the deck. That doesn't mean the beam can't pick up the deck or that the girder can't pick up the deck. It just means that the purlin's kind of main job is to pick up deck. And we could have different loadings. So a tributary width is the same idea, but instead of looking at the entire area, we just break down one component of that area at a time. And sometimes that can be really helpful for us. So if we break the area down to every meter along the element length. So if I had this plan here, I want to know the tributary area, but maybe also the tributary width of an element. So let's talk about RJ01. So this looks like a joist that starts here and goes to here, or that's how long it is. It says that this is 2 bays at 8 meters each. So that gives me the impression that this joist is 8 meters long. So we've got a tributary length of 8 meters. This looks like it's 3 bays that are 6 meters each. So that means from B to C is 6 meters, which means that distance is 2 meters, and that distance is 2 meters, and that distance is 2 meters. So it looks like this tributary, or this joist, is 8 meters long, and it's picking up some part of this deck, and it's picking up some part of this deck. Now, if this was the table, and these were the table legs at one end, and that's the table legs at another end, and that's the table there, what percentage of the table goes to the legs at that end, and what percentage goes to the legs at that end? Intuitively, you know that 50% is going to that end, and 50% is going to that end. So it seems like 50% of this deck is going to go to this joist, and 50% is going to go to this joist. Well, if this is 2 meters, it seems like we're saying 1 meter of this is going to go to this joist. But look, we've got this part over here as well. We've got those 2 meters there. So it looks like 1 meter of this portion is going to go to this joist. So 1 meter here and 1 meter here. 2 meters. That seems like the tributary width of this joist is 2 meters wide. It is picking up 1 meter from over here and 1 meter from over here. Or a tributary area that is 2 meters by 8 meters. So it looks like it's got a tributary width of 2 meters and a tributary area of 2 times 8, or 16 meters squared. And it looks like that joist is identical to all of these other joists. So I think if they're both the same length and they're both the same tributary width and they all have the same load on them, they're all the exact same beam. So we could label all of these RJ01. Let's take a look at another object in this. Let's take a look at RB01. So RB01 spans from grid line A to grid line B. We've already determined that each one of these grid line spaces is 6 meters. So it seems like we've got a 6 meter long beam. So its length is 6 meters. It looks like it's picking up some joists here. So the deck was spanning in this direction, and then this joist, it seems like half of it's going to go over here, and half of it's going to go over here. And half of this is going to go over here, and half of this is going to go over here. Or we could say that we're cutting a line right here. That's our 8 meters. So 4 meters of whatever this is going to this beam. Or that its tributary width is 4 meters. So let's take a look. We have a length of 6 meters and a tributary width of 4 meters. It seems like we've got 24 meters of tributary area for that beam. Are there any other beams that look like they are 6 meters long and have 4 meters of tributary width? I'd say all of those look the same. 6 meters long, all of them, and they're all picking up half of a grid line spacing. Let's take a look at RB02 now. RB02 is also 6 meters long, so in that respect it's the same as RB01, but it's picking up half of this zone, so 4 meters, but then it's doing it again on the other side, so 8 meters of tributary width, all the way from here, all the way to here. So 6 times 8, we've got 48 meters of tributary area. Are there any other beams that look the same as that one? Well, I see this beam is 6 meters and this beam is 6 meters, and they've both got 8 meters of tributary width as well. So it looks like those are only 2 beams now, or are all RB2. So we had all kinds of joists and all kinds of different beams. We now only have 3 things we have to design because most of them are duplicates of each other, all doing the same job, carrying the same load, spanning the same distance with the same tributary width. So we've cut our work down by a drastic amount by being able to identify these patterns. Let's take a look at column C1. Now, there are ways you can do this. You could figure out what tributary half of that is going to this column and the tributary half of this is going to that. I find it easier to just look at the tributary area in whole. We've got that beam spanning and that beam spanning, or half of A to B and half of 1 to 2. Or if we consider this zone here a table with 1, 2, 3, 4 table legs at the corners, the same way we did thinking about this table, you know, a quarter is going to go to each leg. And so a quarter of this zone is going to go to this column right here. Or half of that distance times half of that distance. Or 4 times 3, or 12 meters squared. And look, we have 3 other columns doing the exact same thing. Let's take a look at C2, or the column that's taking place at B1, at grid line B1. Well, it's picking up a quarter of that table, if you want to call it a table, and it's picking up a quarter of that table, if you want to call it a table. They're both the same, or we've, instead of 3 meters, we've got 6 meters by 4. So instead of 12 meters squared, we've got 24 meters squared. Do you see any other columns with the same tributary area? I see this one, I see this one, and I see this one. Column C3. Column C3 is interesting because it is picking up a quarter of this table, we're going to call it a pretend table, and a quarter of this pretend table. So we're saying that it is 3 meters times 8 meters, or also 24 meters squared. So really, its tributary area is the same as C2, and maybe we would even design them the same. I've kept them separate just in case something, you know what, you could make them all the same. There would be nothing wrong with that. They have the same tributary area. Same with this column over here. So we have column C4, which is now picking up a quarter of this zone, and a quarter of this zone, and a quarter of this zone, and a quarter of this zone, or 48 meters squared. And that one is the exact same. So that's how we would do the tributary areas for our purlins, the tributary areas for our beams, and then the tributary areas for our columns. So we're looking at layers there, and I find it helpful to sometimes stop and think about them individually. So here's that worked out where I actually show you the tributary widths and the total tributary areas calculated out for all of those that I just verbally went through with you. What happens when something is skewed? Well, if we look at this beam here, it is picking up half of this joist, and 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 half of this joist. So it's got a tributary width that varies. It's got its tributary length, but then a tributary width that varies. So its tributary area is still calculable, but it's got a tributary width that changes along its length. This one's a good one to look at because look at this. It's going to pick up half of that joist, half of that joist, or this tributary width varies, and then this tributary width varies. These ones, this one throws people off completely. These all have the same tributary areas. They have the same tributary widths because this is, you can actually draw it to scale. That's why sometimes it's helpful to draw it because you can really just see exactly what's happening here. These ones do vary. You can see that those are different, and those ones are going to be the same, and then those ones are going to be the same. So we can still calculate tributary area. If you have an opening, so something open to below, there's no floor there. If there's no floor there, there's no area to pick up. So there would be nothing to take into account. You would have no floor there. A different type of flooring is not an opening. You would have different loads that might be impacting the same area or the same zone or the same element. But an opening to below means that there's no load on it, so there's no tributary area to contribute to the thing you're analyzing. So here, you can see we have an opening to below here. Let's do some examples, and it might be easiest if I stop and show you my my work. Maybe I'll work this out with you. I'm just gonna zip ahead and see if that's gonna be the easiest way for this one. I will talk about the things we're gonna look at. Let's take a look at L2J01, or Level 2 Joist 01. This is a wood building, so that does not mean open web steel joists. But they've told us that they are at 16 inches center to center. So there's a whole bunch of joists framing across this zone. They've told us to look at L2B01, or that beam, and there's 3 of them that look identical. They've told us to look at L2BO2, or those 2 beams that look identical. And they've told us to take a look at L2BO6, or that beam right there. So, I'm trying to decide if it's worth you seeing me do these hand calculations out, because I don't know that it's going to give you much more information than me talking about it. A lot of the times I think there's a huge value in you seeing me work out the calculations, but there's actually not that much to these calculations. I show more in these diagrams than you need to know. Just if you, at the end of the term, want to go back and do some practice work, this is a really good one that you can go back and check out. So don't worry about all of this right now. It might be something that's handy for you to come back and look at the end of the term if you're looking for some extra practice examples. So L2J01. So L2J01 spans from this line to this line. And it says that that is 11 foot 8. So let's calculate that out. 11 foot 8, we have 11. Well, maybe I will do these out for you guys. All right, I'm going to stop this. I'm going to flip my camera down, and I'll do this on a piece of paper for you guys. Okay, so let's start with our very first beam, which is L2J01. So that's this beam over here that spans from this wall to this wall, and it's 11 foot 8. So we know that its length equals 11 foot 8 inches. Well, we find it a bit of a pain in the butt often to work in imperial, so we're going to switch this over to metric. So we're going to, kids take my calculator sometime. We're going to switch this over to metric. We've got 11 times 12 plus 8 times 25.4 equals, so we can plug this into the calculator, 11 times 12 plus 8 times 25.4, we get 3,556 millimeters, or 3.556 meters. They told us that we had L2J01 at 16 inches center to center. So that means every 16 inches there is one of these wood joists. So our tributary width, that means that it is going to pick up 8 inches of deck on one side and 8 inches of deck on the other, or our tributary width is 16 inches, which is the same thing as 16 times 25.4, or 406.4 millimeters, which is 0.406 meters. So we have a tributary width of 0.406, and then let's figure out our tributary area as well. 3.556 times 0.406. 3.556 times 0.406. We're going to get a tributary area of 1.44 meters squared. So we've taken our beam and we know what its length is, and we know what its tributary width is, and we know what its tributary area is. The next thing they wanted us to talk about was 2B01. So that's these three green beams. So it looks like its length is from this wall to this line right here. Well, they haven't given us that dimension, but if we were the contractors, if there's something that we can interpolate from the drawings, they don't need to give it to us. We should be expected to figure out that that distance is 35 minus 11 foot 8. So we should be able to figure that out. So let's take a look at that. Let's do our L2B01. So L2B01. Our length is going to be 35 feet minus 11 foot 8 inches. Well, we already know what 11 foot 8 is. We know it's 3.556 meters. So let's just figure out what our You want another snack, buddy?
Yeah.
Okay. All right, hold on. Sorry about that. My kids are snack holes lately. They just eat and eat and eat and eat and eat. And apparently the 4 snacks I pre-prepared was not enough for them. So we can figure out how long our 35 meters is, or 35 feet is 35 times 12 times 25.4 divided by 1,000. We have 10.668 minus 3.556 meters minus 3.556. We have a length of 7.112 meters. So we have a length for our 2B01. Let's take a look at this. Its tributary width, it looks like it's picking up half of this zone and half of this zone, or a tributary width of here to here. Or essentially, if these were at some distance on center, some equal spacing, we would know that it was essentially half of, or that it's about the similar of that spacing. So half of this spacing and half of that spacing is one whole spacing. So they've said that this entire distance is 45 feet. So 45 divided by 4. Each one of these distances is 11.25 feet. So we're picking up half of 11.25 feet here and half of 11.25 feet here, or a total of 11.25 feet. So our tributary width is 11.25 feet, which is 11.25 times 12 times 25.4 divided by 1,000. That equals 3.429 meters. So we have a length and we have a tributary width. We can calculate the tributary area of this beam is 7.112 times 3.429. Let's plug that into our calculator. 7.112 times 3.429. We get 24.4 meters squared. They wanted us to take a look at L2BO2, or these two beams here, that span from here to here. So we know that we've already figured out that distance. Each of those distances was 11.25 meters. So we're talking about L2BO2. The length was 11.25 meters, or 3.429 meters is the length. So now we need to figure out the tributary width. So this one is interesting because it's definitely picking up half of our L2JO1, and it's picking up whatever the half of the distance is between these L2JO2s, which are at 16 inches on center as well. It doesn't say it, I'm telling you that, I'm giving you that information. That 8 inches, though, doesn't seem like that big of a deal compared to almost the 6 feet here. You can definitely include it. It would be more right, for sure. So what I'm saying there in that example is that if this is our beam, we've got all of these joists framing into it. and half of it is going to the beam. Oh. So we've got our beam here, and these are all the joists, and half of it is going to this beam. And then over on the other side, we have all kinds of these joists that were at 16 inches on center. So technically, we have this 8 inches right here as well. I would be okay with you including that or not including that for something this small. If these were open web steel joists that were at 2 meters on center, no, we definitely want to think about including that. But 8 inches, I'd be okay with that. I can't even remember what I did in the example, to be honest. I'm in fact gonna flip ahead and see and maybe do the opposite of whatever I do there. So remember, there's all kinds of information in this that you guys don't need. This is stuff that you will be able to figure out by the end of the term. Right now, all I'm looking for is the tributary width, and then I'm doing the tributary area for you right here. It looks like I did include the 8 inches. So we'll do the same here. So our tributary width is half of the L2J01s, which we know were how long? 3.556 meters long. And then half of the 8 inches in between these. So we can calculate that tributary width. Tributary width. So tributary width is 3.556 divided by 2 plus 0.406 divided by 2. This is from L2J01, and this is from between it and L2J02. We can calculate that, and we get 3.556 divided by 2 plus 0.406 divided by 2. We get a tributary width of 1.981 meters. Often for analyzing these sorts of things, what we really need is to know tributary width, but I'm doing the calculation for tributary area as well, just to help give you an idea of what that looks like. So just for completion, let's do the tributary area of this as well. Or 3.429 times 1.981. Or 6.79 meters squared. L2BO6, we have half of our L2JO2. So essentially half of the tributary area that these L2BO1s had, and it is spanning 5'10". So we are now doing L2BO6, and its length is 5'10" inches, which is the same thing as 5 times 12 plus 10 inches. So we have 70 inches times 25.4 is 1,778 millimeters, or 1.778 meters. So that's how long our beam is. And our tributary width, we determined, is only half of that 11.25 feet, or 3.429 divided by 2. 3.429 divided by 2, or 1.714 1.5 meters. And our tributary area is going to be 1.778 times 1.715 or 3.05 meters squared. So this is just to try to show you tributary width and then also simultaneously tributary area. You're going to do some calculations of this in your assignment. You can see here that I've shown you these tributary width calculations. Don't worry about all of this. Like I said, that's what we're going to do by the end of the term. Okay, let's talk about the project now for a minute. We'll switch this back to looking at me. I know you've missed me. Let's bring this camera back around. It's not the most elegant solution, I apologize, but it does the trick. I'll turn some light back on. I know it makes me a bit brighter, but I can see a bit better now. Okay, so I have posted your projects for you. You obviously don't know how to do them yet. There's a lot of information you don't understand, but it's to help get you thinking about them. And I gave you some kind of ideas for dates on where you should be. You know what, I'm a procrastinator. I would probably wait until the last minute. I'm not recommending that. Don't do that. Please pretend you didn't hear me say that. You should definitely follow these dates that I've suggested as guidelines. So this is a PDF that's been uploaded to Quarkus for you in the project module. There are two parts, like I've said. This is the creative side. The idea here is that you guys all have a creative vein, or else you wouldn't be in this this discipline that you're looking at. And I don't want you to get uninspired if you have a creative side by being in this class. So I want to try to balance the math and what I find very interesting with what I know you really want to be studying while you're here. So I have added a component to this project that lets you be creative. So you get to pick an everyday object and think about it when it is not moving, and all of the loads that might be applied to it while it's not moving. These do not need to be the building loads, but you should be thinking about the worst case loads of that type. We're going to talk a lot about loads on buildings, and maybe some of the building loads are applicable for you. That's going to be up to you to outline. You're going to do some sketches of it. This is a chance again to be creative. And you want to be thinking about its position in space, and where does it sit, and how does it sit? If it gets picked up, where do you pick it up? Because those are all the reactions on the object. So there's all the loads that are applied to it, and then there are the things that stop it from moving. So if I pick up my coffee mug, it is filled with coffee. But when I hold it, my hand is what stops it from falling in space or tipping over. My hand is the reaction for the cup. So start thinking about that, because then you're going to take your beautiful drawings and you're going to turn them into structural free body diagrams, which is literally that beautiful object turned into a stick figure with all the loads as stick figures and all of the reactions as stick figures. And you're going to have to do that for all of the different load types that you can think of. And then you're going to talk a little bit about those loads and what that looks like. Part 2 is going to be, I have posted an arena project that you are going to draw shear and moment diagrams, free body diagrams of those objects, and you're going to analyze them, or at least the first half of analyzing them. All of that's going to become clear as we go through the term. One of the things you're going to do is look at the tributary width of your beams. So you've already got some portion of it that we've already talked about today that you can now do. Don't worry about it. Don't jump the gun on that. You can let it all sink in and see how it all goes together. You're eventually going to actually be producing for those beams something that looks like these, except you are going to have to, instead of using these handy little equations, have to do something called method of sections, because I need to test you on method of sections in this term. When we do structures 2, we can drop the method of sections process and you can use these handy little equations. But for you, for your project, you have to do method of sections. And then I've listed out what you have to do for all of those elements. Again, that's going to become much more clear as we get closer to the end of the term. The due date isn't until the very last day of class, but you have your exam before that. And I find the people that have at least taken a crack at the project do much better on the exam. Maybe you don't have time to finish it, or at least part 2, but you should take a look at part 2 and get your head around it, because you're going to find it's a good studying technique for the exam. So that wraps up today's lecture. You should be able to produce structural drawings. I know, probably not yet, but you should be on your way to thinking about structural drawings. You should definitely be able to calculate tributary width and tributary area of elements, especially the more basic ones. There is one in your assignment that is slightly more complicated. Take your time, think about it. I'm not giving partial marks. There's a right answer for that one, and you're going to go through and you're going to do it and you're going to practice it and you're going to try to get it right. Talk to your friends. Try not to just share answers. Try to actually think about it a little bit. And you have TAs that you can ask help from. But I want you to be able to work on calculating tributary areas of things. And remember what I talked about open areas on floors. Okay, so that wraps up week 2. And next week we're going to start talking about buildings and how they go together. Again, it's a bit of a snooze fest. In fact, next week is literally just a bunch of slides with lists on them. So I apologize. Make a drink of coffee beforehand, pop some popcorn, get ready to just try to absorb the information. I apologize, it does have to exist as a lecture, but we'll try to make it somewhat interesting if we can. Okay, see you next week, team.